Sorry, I have a call uh, from my senior. So sorry for interruption. So I think Murmu ma'am. Hello,
Yes,
hello,
sir. Yes, sir. Okay, sir, tell me.
hello, hello.
Hello? Yes,
Huh,
sir.
can you hearing me?
Yeah. It is
Okay.
audible.
Yeah. Okay, ma'am. Sorry for interruption because
Hmm.
I have a call from my senior. So
Okay.
can I close this session because uh, I have a flight announcement, half an hour or maybe 45 minutes. So if you don't mind,
Okay, sir. 20, 30 minutes you can't take, means before the boarding.
yeah,
Uh,
I can.
if you will
So
discuss about that field experience, this is benefit for them also. That's what.
okay. So my experience, okay, good.
Your
This is
experience
my
also
with
and
Ultratech.
manufacture. Huh,
Yeah,
with
with
Alta.
Ultratech. Okay, good. It's an opportunity for me. Uh, okay, brothers. Okay, friends. Uh, Basically, I'm a civil engineer and I have done my civil engineering from Rajasthan, Kota in 93, 94. And before Ultratech, I was with a small construction company in Mumbai, and then I have started my career with Rajasthan State Bridge Corporation, uh, and then I have joined the Ultratech Cement Company with a very low profile, and now since 27 years I am working with Ultratech Cement, and it is a single cement company which I have joined. There is no change in past 27 years because it is a very very respective area. Yeah, very respective work environment in Aditya Birla Group, and they are taking care of all the personal and professional needs. So that is the reason I have not changing the company. And you all know about Ultratech Cement and Aditya Birla Group. Ultratech Cement is a unit of Aditya Birla Group, and we are producing uh, 150 plus, almost 150 million ton per annum cement production. We are producing cement, and now we are going for a solution provider company because we have other division which is Ultratech Building Solution. One is Top Shop. Then another one is the building products, which is waterproofing products. And third one is the digital platform. It's called UTech by Ultratech. So now we are going as a solution provider company. And in Chhattisgarh, we have four units, and we are producing about 12 million ton per annum. And we are associating with all government bodies and all builder community institutions, uh, individual house builders, architects, engineers, and we have RMC plants also. In Pan India, we are producing ready mix concrete also on a large scale. Uh, so now Ultratech Cement Company is not a cement company. Now Ultratech is a solution provider company. Uh, we have very very much concern about our customers, about our influencers. So we are conducting on regular basis some of training
Respected
programs.
sir, your slide is not visible, sir. Sir, slide is not visible.
Oh, slideshow is over.
Okay,
Slideshow is
okay.
the over. Okay, yeah,
Okay,
yeah.
okay.
I think yeah, have you have joined slightly late, maybe, maybe.
No, no, no. I have joined on time, sir.
Okay, so but
Now your
Meena,
slide is not
no, no,
visible.
no, but I'm not showing right now any slide.
Okay, 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 okay.
I have
Okay, sir,
already
clear.
done my presentation,
Okay,
and
okay, 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 okay.
yeah, yeah. Thank you so much.
Okay.
Thank you for concern. So, think we are conducting so many trainings programs for individual house builders, engineering college students, builders, architects, engineers, influencers, and we have a very new concept also that's called Center of Excellence, and already we have made in NIT Raipur one Center of Excellence, and in totality we have 250 plus Center of Excellence in Pan India, where we can use the Center of Excellence for the students training, masons training, ISBs training, and contractors training, and product display of Ultratech cement. So these type of activities can help to develop our day-to-day construction habits, day-to-day technologies, and we are very much associated with all the professional institutes in Pan India, not in Chhattisgarh, Pan India. So now our vision is 200 million ton per annum for 2027. So uh, we are sure to achieve this milestone with Ultratech Cement and Aditya Building Group. That's all from my side. Thank you so much. Thank you, ma'am. Thank you. Thank you. Thank you all. Thank you, Meena ma'am.
Thank you, sir. Thank you.
Over to you. Over to you. Over to you.
Okay, sir.
Shall I leave, ma'am? Thank you.
Okay, sir. Thank you. Thank you.
Thank
Thank
you.
you.
Good night. Good night.
Good night.
Thank you, sir.
Okay, dear participants, sorry for Sarhej, maybe some other session, so that's why he left. So we'll discuss about IS code 10262 2019. Is it okay, or hello participant, or we'll wait for Canada's speaker? Hello.
As your wish, ma'am.
I can
Yes, sir,
explain, not a
completely
It's
fine.
okay,
problem.
ma'am.
Ma'am,
What?
please
Madam, we
explain,
can have
ma'am.
a break.
Okay, break.
No, no, explain, ma'am.
Uh,
Explain. IS
okay,
10262 2000.
Yes, sir, please, ma'am, explain.
okay. Wait for some time. I am. explaining. Is it visible?
Yes, ma'am.
Okay. So in our IS, visible no? Visible no?
Yes, ma'am. Yes, ma'am. Slide is visible. Visible,
Okay.
ma'am.
So in our IS code 10262 10262 2019, earlier it is 1982, then 2009. So in 1982 we have a graph. Here in 2019 also we have a graph that cement strength, a mortar strength in 1982 and water cement ratio. And now it is changes each. This is our graph, 28 days compressive strength of concrete and water cement ratio. So from here we are calculating the water cement ratio. Suppose whatever target strength we are taking, and the x-axis we have a water cement ratio, and according to that we'll finalize the water cement ratio. And in these three curve are there, curve 1, curve 2, curve 3. This is OPC 33, 43 and 53. And suppose we are nowadays we are taking the pozzolanic cement also. So that one is suppose that expected 28 days compressive strength. This is about our OPC. And suppose other than OPC, then we have to assume like this. The absence of the actual 28 days compressive strength, curve 1, 2, 3 may be used for OPC 33, OPC 43 and 53. So depending on the compressive strength of that cement, according to that we have to take. And maybe most of all us are the faculty, so we know the how we'll design the concrete mix. So I will give the overlook of all the mix design, whatever appendix it is given. Normal strength. Then we are adding the pozzolanic materials, another appendix. Then we have the high strength concrete, self compacting concrete, mass concrete. So we'll touch all these mix design. So normally whenever we will start the mix design, we will calculate the target strength, and target strength is based on this two formula. That one also we know, all of us. FCK dash equal to FCK 1.65 S, or FCK dash equal to FCK X. So FCK is the characteristic strength, and FCK dash is your target strength, and S is here, it is standard deviation, and X is the factor based on the concrete as per the table it is given. And standard deviation we are this is from statistical point of view, how many number of sample we have taken. From that we will calculate the standard deviation. And this is 1.65 statistical value. This is given in the 1982 code. Why we are taking only 1.65? As per the definition, characteristic strength is that if we are taking the 100 number of sample, 95% will be passed. So 5% result will be fail. According to that 1.65 data is came. Okay. And after that, target strength will finalize the target strength, and according to the target strength will finalize the water cement ratio. And based on the size of aggregate, we are assuming we are taking the air content, and it is given in this table 3. For this is normal. So whenever you will go for the high strength concrete, the table is different. Then after that, we will choose the how much water quantity is required. Normally for normal concrete, this is given for 50 mm slump. We'll refer the table 4, and 10, 20, 40 maximum size of aggregate. According to that, water content will be maybe 165, 186, and 208 in reverse order. For 40 mm this is, 10 mm this is, and 20 mm this is. For this, we'll take for 50 mm slump. Suppose slump is, we are taking the 100 mm. Yeah, we are taking the 90 mm. Yeah, we will take the 70 mm. So depending on that slump value, yeah, requirement of the slump, we can change the water quantity, and that yellow line may be visible to all of you. So here it is for 50 mm slump. Yeah, other than 50 mm slump, we have to decrease the 3% or increase the 3%. Every increase of, yeah, each increase or decrease of 25 respectively. Suppose we are 25 mm slump we are taking, so 3% water we have to reduce. Suppose we are 75 mm slump we are taking, 186 of 3% we have to take. So this maybe all we know. Again, I am revise this one. Then here it is given that how much percentage of GGBFS fly ash we are taking. That one is also given. Another important point is coming whenever we'll do the mixed design. This is the highlight color. One is given how much quantity of mineral admixture we are adding. And that day some participant has asked about that plasticizer also. Here it is given plasticizer, how much you will reduce. That one is also given in the code only. Code itself, it is given. Suppose you are using the high reducer water, here it is given IS 9019103 water reducing admixture or super plasticizing admixture usually decrease water content 5 to 10% and 20 to 30%. This is as per the code, but nowadays invention is going on higher, so that super plasticizer may reduce to 40% also. So as per the trial and error, hit and trial, we can adjust the water quantity. After mixing a mixed design casting only, we can adjust that how much it will reduce the water quantity. Next is important one is estimation of coarse aggregate. So estimation of coarse aggregate, we have to refer the table 5. Here table volume of coarse aggregate, and whenever we will design the concrete mix, 2 types we have to design for. Suppose normal concrete, non-pumpable and pumpable. Pumpable means we have to transfer the concrete through the pump, and non-pumpable we have to transfer the concrete through chute also. And in non-pumpable concrete, normally we are use the aggregate 100%, but pumpable concrete if you are using, then we have to reduce the 10% and 90% aggregate we have to use in aggregate, both in combination of fine aggregate and coarse aggregate. So here as per the table 5, we have to calculate the volume of coarse aggregate per unit volume of total aggregate for different zone. Depending on the zone, we have to calculate the volume of coarse aggregate in both aggregate, in combination of fine aggregate and coarse aggregate. So here it is given 4 different type of zone as per the building, and for whenever we will go for the road construction, there it is 3 type of zone. Zone 4 is not there, and you have to refer the IRC 44. So for that you can refer 44. So here it is zone 1, zone 2, zone 3, zone 4. As per the sieve analysis we can get, and as per the zone 2, suppose for example we are taking the zone 2, and we are taking the maximum size of coarse aggregate is 20 as per the 20 mm, and here it is coming 0.62. And suppose, for example, you have taken the 30 MPa characteristic strength 30 MPa, yeah, M30 grade of concrete you are preparing, then our target strength is coming 38. And for 38.25, suppose here it is our, and OPC 43, for example, we are taking. So here it is nearly 38.25. So nearly it is coming in between the 0.4 and 0.45. So 0.4 and 0.45, we will take, suppose, for example, 0.42. And as per the table, it is coming 0.5 water cement ratio. So for 0.42 water cement ratio, we have to recalculate the volume of coarse aggregate. So here it is mentioned volume of coarse aggregate per unit volume of total aggregate for different zone of fine aggregate for water cement, yeah, water cementitious material ratio is 0.5. And now we have taken our water cement ratio is 0.42. And here another condition is also coming whenever we will talking about the 0.42 water cement ratio, and this should be as per the previous IS 456, their table 5 is given. So so here suppose we are, this is table, we have to cross verify with the table 5 also. So this side is given reinforced concrete, this side is given plain concrete, and we design for the reinforced concrete. So here M30 we are talking, so maximum pre-water cement ratio is 0.45. So as per the curve we have taken that in between 0.4 to 0.45. So it is whatever we have water cement ratio we have adopted, this is less than the 0.42. And that's why according to the 0.42, how much coarse aggregate we have to have, what is the volume of coarse aggregate we have to take, that one we can choose from the table 5, and we have to recalculate also. So this is given in the code only. Here this, whenever we'll table 5 for water cement approximate value of the for this aggregate volume are given in table 5 for water cement or cementitious material ratio is 0.5, which may be suitable adjusted for other ratio. Suppose we have taken the 0.42, so for every change of the proportion of the volume of coarse aggregate of the total aggregate is increased at the rate of 0.01. For every decrease in water cement or cementitious material ratio 0.05, and decrease at the rate of 0.01 for every increase in water cement ratio. So now our water cement ratio is 0.42. So from 0.5 it is lesser than 0.08. So for 0.08 by interpolation, we can increase the volume of coarse aggregate 0.62 as per the zone of the two. So here approximately we can increase 0.02. So 0.62 plus 0.02 maybe 0.64 is our volume of coarse aggregate. And suppose we are taking the non-pumpable concrete, we are preparing the non-pumpable concrete, that fine aggregate is 1 minus 0.64. So fine aggregate equal to 0.38. And after that, you have to we have to calculate the volume of aggregate in concrete. So volume of concrete is 1 cubic meter. So 1 cubic meter, we are preparing for the 1 cubic meter. So 1 minus volume of cement, volume of water, volume of super plasticizer, and volume of water content. So it will give the volume of aggregate, and volume of aggregate is a constant, and volume of here from all in aggregate we have calculated the volume of coarse aggregate and volume of fine aggregate, and by multiplication of the volume of coarse all aggregate into volume of aggregate into density into 1000, whenever you will multiply, then you will get the quantity of aggregate and fine aggregate and coarse aggregate. Another important thing is coming. Suppose up to this it is clear, no? Hello.
Yes, ma'am. Clear.
Okay. So suppose
yes,
we are okay. So water absorption. Another point is coming: water absorption and your moisture content. So in dry in summer season, your coarse aggregate will absorb more water. So what we'll do, yeah, normal day also water absorb, there are little bit, yeah, some quantity of water will absorb. So we have to adjust that water quantity, and how you will adjust, this is given in your here also. So we have, this is the formula. We have calculated the, suppose this is the after the mixed calculation. Cement, for example, cement is this much, water is this much, fine aggregate this much, coarse aggregate is this much, chemical admixture, and free water cement ratio. Suppose we are in dry condition. So, and normally whenever we'll design the concrete mix, we'll take the coarse aggregate, yeah, aggregate for surface saturated dry condition. Surface sorry, surface saturated dry condition means we'll calculate the specific gravity for, will aggregate will be saturated for 24 hours, and then we'll dry the sample for surface dry, then we'll keep the uh, aggregate for oven dry, and after that we'll calculate the specific gravity. So whatever mixed design we are doing, we are calculating the mixed design as per the surface saturated dry only. And field people are using in dry condition. So for dry condition, what is the weight of aggregate we have to calculate? So mass of fine aggregate in SSD condition divided by 1 plus water absorption divided by 100. So it will 648 as per the surface saturated dry, and as per the dry condition it is coming 642. So our weight of the quantity of the aggregate is reducing. So for both, for coarse aggregate also we have to calculate both. This is the example for both coarse aggregate also reducing. Then how much mass is reducing, that one you have to calculate. So for coarse aggregate it is 6 kg and fine aggregate also 6 kg. So this one is your quantity of water it is absorbing. So this, so we have to calculate the, yeah, we have to add the 12 kg of water extra. Whenever it is water absorption are there in coarse aggregate, then we have to calculate the, yeah, we will readjust the water quantity. And suppose moisture is there. So is it clear now? Up to this clear? Hello?
Yes, ma'am.
Suppose okay. Suppose moisture is there, then we have to calculate the fine aggregate in wet condition. What is the wet condition of the fine aggregate? Suppose moisture are there. So mass of fine aggregate in SSD condition into 1 plus free surface moisture divided by 100. So we'll get the, earlier it is 719. Now it will be 748. So here your weight of the aggregate will be increasing. And for coarse aggregate also same. So we have to readjust the water quantity here. So in that case, whatever water quantity you have got and what is the difference it is coming, we have to reduce that one. So whenever dry condition we are using, this is simple only, that thumb rule only. When water will be absorbed, we have to add more water, and when moisture are there, we have to reduce the water. So calculation will be like this. Okay, clear? Key point only I am explaining, because we'll join for another also, and we'll discuss full IS 10262. That's why I'm going fast. Another point is coming when we'll calculate the pumpable concrete. Suppose pumpable concrete we'll discuss, then for pumpable you have to take the 90%. Here it is given. For pumpable concrete, we have to reduce the 10% of the coarse aggregate. So this is for your normal concrete. And whenever you will add the, suppose pozzolanic materials, suppose you are adding the pozzolanic materials, then we have to calculate, suppose fly ash we are adding, then only we have to calculate the cementitious material. And if you are adding the GGBFS, yeah, metakaolin silica fume, then we will consider as a 100% only. Suppose fly ash you are adding, then 10% cementitious material we are considering. So we have to calculate the cementitious content. %, here we can see cementitious material content equal to whatever cement content you have calculated, there you have to add the 10% extra. So it is 474. And after that, how much you are adding the fly ash? Suppose fly ash you are adding the 30% or 20%. According to that, you have to divide. Now it is GGBFS same only, but here we are not calculating the cementitious material. We directly will add suppose 30% or 40%. In terms of cement, we have to replace. Then next is coming your high strength concrete. So in high strength concrete, your design is little bit different. So for suppose M's, and here we were using we have to use mainly one is chemical admixture, polycarboxylate, ether waste, superplasticizer we have to use. And another each table is different. For normal design, we are using the graph, but here as per the target strength water cement ratio, we have to finalize, and different table is given. Okay, so this is for your high strength concrete, how you will water cement ratio you will take. So for normal concrete, we refer the table, curve. But for high strength concrete, we have to here target strength, whatever target strength we are taking. For that, we have to use this water cement ratio. So it is started from 70 to 100 is given, and depending on the size of aggregate, coarse aggregate 10 mm, 12.5, 20. Suppose you will design for the 100, yeah, 90 something is your target strength. Then water cement ratio you have to take the 0.24. And another important point is for this we have to use the M53 grade of cement. OPC cement is better. and here we can make minimize the our max as per the 456 also. If we are using the OPC cement, then maximum cement content is our 450 kg. So we have other use of pozzolanic material will not achieve that quantity of cement. So for that cases, we have to add the different type of pozzolanic materials, maybe fly ash, granulated ground GGBFS, ground granulated blast furnace slag, metakaolin, या silica fume, and this is given the how much ratio we can use it, how much proportion. Then here table is also there we have used the refer the table 5 whenever we'll calculate the volume of coarse aggregate. Here volume of coarse aggregate will be calculated based on this based on the zone of the sand, zone 1, zone 2, zone 3, and zone 4 is too much finer. So for that in high strength concrete we are not using the zone 4, and for water cement ratio 0.3, and same only for changing of water cement ratio we have to increase and decrease, and rest are same. We have to calculate the volume of coarse aggregate, volume of fine aggregate, and quantity of coarse aggregate and fine aggregate. Clear about the high strength concrete? Hello?
Yes, ma'am.
Yes, ma'am.
Okay. So next one is our next is coming our self-compacting concrete. That day sir has explained no self-compacting concrete. So self-compacting concrete here this is the criteria for where these 4 criteria is there: filling ability, passing ability, segregation resistance, and viscosity. Filling ability, flow ability, passing ability by B funnel, filling ability by your table, and segregation resistance, and viscosity. And here the different type of that one also that they sir has discussed. That's SF1, SF2, and SF3. What is the ranges of slump flow for SF1, SF2, and SF3? Here it is given, and here it is given for which type where we can use. That one is also here it is given. And here what is the requirement of L box? L box normally your horizontal height whenever we will pour the concrete. So what is the horizontal height and vertical height? That ratio each it should be 0.8 to 1. Then next is your segregation resistance. Using the 4.75 we have to sieve, and that how much percentage passing retained, that one you have to calculate. Then next one is your V funnel. That one also sir has already discussed. Main is the how we'll design it. That one we'll discuss. So here little bit design is different as per the normal concrete and high strength concrete. It is fully different. There we are using the as per the water cement ratio we are calculating, but here first of all we have to calculate the we have to assume the water quantity. So for trial typical range of mixed constituent, here normally it is suggested that 400 kg per meter cube to 600 kg per meter cube we have to require the fine Then water content between 150 to 200. Another is modifying viscosity modifying admixture. We have to use high range of water reducing like polycarboxylate ether based high range water reducing admixture. And sometime also we have to use the BMA that they already sir has discussed. Suppose we will not using the other finer particle, yeah, fly ash, then we can use the BMA is the compulsory. Yeah, we can use, if we will use, then it is good. So here mixed design will start from the this is your M30 grade, whatever grade you are taking, not a problem. As per that M30 grade, this is your water cement ratio. But here you have to left that one as per the slump flow, whatever ranges is given. Here it is mentioned for slump flow 750 to 850. So there we have seen that 19, how much we have seen, maybe up to 210. So it is in between that one. So it is taking slump flow 3 is your higher one. So water will start from 190 kg. There, as per the course aggregate, we are assuming the water quantity as workability. Here directly we will start as per the slump flow value. Slump flow value, whether it is lower, yeah, higher, yeah, higher, yeah, medium. So for that we have started 190 kg of water cement ratio. Sorry, 190 kg per meter cube is your water, and water cement ratio is our 0.43. Corresponding to this, the water content is 190 kg, will corresponding to the cement content is 442 kg. And the content of 442 kg per meter can be further divided into a OPC. Generally fly ash content is 25 to 50 in our SCC, self-compacting concrete. But whenever you will go for the high strength concrete, then normally if you are adding the self fly ash, then your strength will be reduced. And suppose you will go for the high strength, then we can add BMA with your silica fume also. So here this is your fly ash and cement content. Then selection of admixture, that one is as per the cementitious material we can take. But next thing is coming our powder content. That one already we have discussed, 400 to 600 kg. And now here we have taken the 442 is our powder content as cement content. So the powder content fine less than 0.125 mm required for a SCC is generally the range of 400 to 600 kg. And since SR of class 1 and viscosity of V1 is required, the mix shall be sufficient cohesive having enough fines. Therefore, powder content equal to 520 kg per meter cube is selected. We require the for this much of SR1, yeah, shrinkage resistance, segregation resistance, and your viscosity V1. We require the 520 kg per meter cube is required. For this, from where we'll get our powder content. Yeah, powder content is 442. So 520 minus 420, 520 minus 442, we have to deduct. So this one is your 78 kg. So that 78 kg will collect from the sorry, collect from the fine aggregate. So the fine aggregate has a 8% materials less than the 0.125 mm, and therefore fine aggregate quantity 78 minus 0.08 975 kg per meter cube. Are you understood this sentence, or I will explain? Is it okay? How it is
Yes,
coming?
ma'am.
Okay, there. Thank you. Okay, so mixed design we can do like this. After that, simple calculation only. After that, this is the volume of coarse aggregate you have to calculate, and this calculation is same only. Any doubt up to this?
Hello.
Yes, sir.
Am I audible?
Yeah, you are audible, sir.
Yeah, I am Dr. Dada Patil from Mumbai. Actually,
Yes, sir.
I have one question in this table number 5 IS 456 2000.
Yes, sir.
They specify minimum cement content as per that exposure condition. Oh, yeah, right. This one. So
Minimum, not sir.
whether it is
Minimum, maximum.
minimum here. No, minimum 300, 300, 320, 340, 360.
Okay,
This is there,
okay. Yeah, minimum cement content. Yeah, yes.
So
That one is also we have to check.
No.
That one I have missed. Yeah.
No.
Tell me.
No,
Yes,
please
sir.
listen
You
to my
can.
question. So my query is whether it is cementitious content or cement, because I am no one is. I mean, of course, when I even did my PhD, I used more than minimum because grade was high. But minimum cement content मतलब ये सिर्फ सीमेंट है कि सीमेंटेशियस चलता है, क्योंकि कुछ लोग बोलते हैं कि आप 260 भी सीमेंट डाल सकते हैं और ऊपर का 40 डालेंगे तो 300 होगा. तो I mean, still it is not clear. So what is your view? Because no one is able to clarify that my doubt.
Minimum.
Ma'am, excuse me. Ma'am, excuse me. Can I
Yes.
interfere here?
Yeah, you can interfere.
Sir, for
You can
table
interfere.
5, for table
Ah.
5, it is always cementitious material, binder. It has been written in the footnote. If you enlarge the table, no, you will find in the footnote itself. It is cement plus SCM, OPC plus SCM.
That means, sir, here if it is, for example, severe 320 means I can put 280 plus 280 cement plus 40 I can put
Yeah.
ply like that. Am I right?
Oh, yes, OPC plus SCM. OPC plus
Because here at
SCM is equal to binder. So here
that's
water
okay, but-
binder ratio.
That's okay, but here at the top they have written minimum cement content. So I think
Sir,
they must have written.
no.
Footnote. It is written in the footnote. Footnote. Notes are there in the bottom, at the bottom. It has been written that it is wherever SCM is there, you should consider OPC plus SCM as a cementitious material. It is written in the footnote.
Okay, that means cement we can go below 300 also like that, 320 also like that.
Yeah, obviously, sir. It is always binder. Cementitious means binder. OPC plus
No, but
SCM.
but maximum is 450 cement. That is for sure. OPC 450, more than 450 kg per meter cube, we don't go maximum. Am I right, sir?
When it is absolute OPC, you should restrain to 450 kg per cubic meter.
No.
Yeah,
But
without
when,
SCM.
but even
Sorry,
when binder is but
Okay.
even when I think binder, suppose we want 700 total binder, but in that also OPC should not be more than 450. I think.
Yes,
Yeah,
yes.
OPC should not be more than 450.
That is
It is
clear
it is
for me,
from
but
the
this.
It is from the
Hello.
perspective of heat of hydration.
Yes, correct. Because cracks will come.
To limit the
Yes.
heat of hydration, it has been limited to 450 kg per cubic meter.
But here I was under the impression that minimum cement content means it is OPC. But maybe I mean it is combined, means OPC plus this one, matlab fly ash or GGBS or whatever.
In notes you can magnify and read the notes, footnotes.
Yes. It is there.
Yes, sir.
Yes, sir. Thank you, sir. Thank you.
Yeah, thanks, sir.
What is your good name, sir?
Ma'am,
Yes, sir.
Tejas Padalkar. Hello.
Yes, sir. You can.
Ma'am, here one point I would also like to highlight.
Yeah.
In case, am I audible, ma'am?
Yeah, you are audible.
Okay. While designing our ordinary grade concrete, I mean not high strength concrete.
Ordinary, normal
Yeah.
strength.
Normal grade concrete up to M40.
Yes, sir.
You mentioned that we have to take the water cement ratio from this table 5, but
Yeah.
it is not so. It is not so, ma'am. Table 5 is explicitly for the durability perspective.
Yeah, table 5 is durability. I have not said like that. We have to take from table 5. We will check from curve only, but we have to cross verify with table 5 also. That maximum pre-water cement ratio should not be more than that one. That one I have mentioned.
Agreed. But here, ma'am, one interpretation is always being done wrongly by various, varied experts, civil engineers also. If you can see, ma'am, the minimum grade of concrete they have mentioned, the minimum grade of concrete.
Yeah, minimum grade of concrete.
Against 5 type of exposure conditions.
Yeah, okay. 5 type of exposure condition, and suppose you will go for the M10 and M15. Yeah.
No, ma'am. That is where the civil engineer makes the mistake. Minimum grade of concrete is to be read separately against the exposure condition. If you want to have the check for the maximum water cement ratio, then it is not against the grade of concrete in this table. For having that check of maximum water cement ratio, you need to know the exposure condition of your concrete structure.
Yes, sir. That one I have not. Tell me, sir.
Yeah, I'm not pointing your mistake.
No, sir. No. Yeah, sir. You can explain.
It is the mistake being made by several civil engineers that minimum grade of concrete is separate from the minimum cement content and maximum water cement ratio. It has not to be read in conjunction with the cement content and water cement ratio. You got my point, ma'am?
Yes.
It is minimum grade of concrete has to be read against the exposure condition, provided that we know the exposure conditions of the structure of concrete under consideration.
Yes, sir.
It is not to be mingled. It is not to be mingled with minimum water cement, minimum cement content and maximum water cement ratio. Grade of concrete not to be mingled with these three.
Sir,
yes, sir. That's correct, sir. Sorry to interfere. That means that is okay, because for example, if it is very severe exposure condition, if you are constructing, that means minimum they say that you don't go below M35. At least M35 provide karo. Very severe exposure condition hai to,
yes,
that's okay. But for example, if I am but for example, if I am constructing my building in Sangli or Kolhapur in Maharashtra, where the condition is not severe, but still there we can go up to M50. That means it is not that some people may misinterpret matlab ki वो मॉडरेट है तो हमको M25 ही करना है, वो भी कुछ लोग बोलते हैं, वैसा नहीं है. We can go higher, but they have told minimum and it is only connected to exposure condition.
Yeah,
That
yeah,
is clear, sir.
minimum.
That is,
Okay, okay, okay.
Ah,
That
that
is-
is that point is clear.
that is
This
quite clear.
table
But what
is
I
for
want to say is-
exposure condition only, but for we should mention that point. Whenever we will design, we have to recheck the cross verify the maximum free water cement ratio also, and in left hand side it is given the your exposure condition also.
Exactly, ma'am. I will explain a brief of my point. Suppose, for example, if we consider the severe condition of exposure, which we already know that whatever concrete structure is being constructed will be having severe exposure condition, then under the reinforced concrete, okay, we see the minimum cement content as 320, maximum water cement ratio as 0.45, but it is not related to M30.
Yeah,
People make some mistake that for M30 we need to have 320 kg of minimum cement content and 0.45 as maximum water cement ratio. That should not be the case. That is what I am into
no,
say.
this is this table is for especially for your exposure condition only. Whenever you will design,
Yes,
so
and
you
for-
have to check
Yeah,
this
yeah.
one
It has
also.
nothing. Yes, it has nothing to do with the strength and water cement ratio.
Strength
It is explicitly
depend on your
explicitly
exposure condition.
exposure condition, and that we need to know. Then only we need to follow this table. If I don't know the exposure condition of the structure being considered, I mean being constructed, then it is no point referring this table.
Table.
That we should already
Yes,
have
sir.
access.
Sorry for the interruption, sir. Sorry for the interruption. I am Ashok from Mumbai University working. Sir, basically,
Yes, sir.
while you are doing the design of the concrete mix, no, first you need to decide the what exposure condition you are going for the concrete
Yes.
mix design. So based upon
Yes,
that
yes,
only,
perfectly.
only you have to refer this particular the table.
Table.
Okay.
Perfectly.
So
Perfectly.
that is the use of this use of table, because basically this table number 5 shows only for the durability of the concrete structure where you are
Perfectly.
that concrete structure is
Perfectly.
exposing. Okay, so it is
Perfectly.
right thing
Perfectly.
actually. Yeah.
Yes, sir.
Sir,
Okay. Thank you.
whenever we'll concrete mixed, we'll do the mixed design. There we should, client has given you that exposure condition also. Yeah, as per
Yes.
the location also you can take the exposure condition. So
Yes,
we
yes.
have to
Yes, yes.
refer this table also
Yes, for the checkpoint. This is the
for the
checkpoint.
checking only, checkpoint only.
Yes, yes. Yes, ma'am.
And that's why IS 10262 also mentioned that water cement ratio is your lesser than this much only. Boundary line. That as per the curve we are taking, this is adopted value, no sir. Whatever as per
As
the
per the
target
curve-
strength we are for me it is 0.42, for you it is 0.43, but one boundary line should be there, no sir. Benchmark is there.
Yes, ma'am.
Ma'am, whatever
Yes,
you
ma'am.
are
As
saying,
per the
absolutely
curve,
you are
we
right.
take as per the curve, the water cement ratio is related to the strength, but
Yeah,
here
related
it is
to-
related to durability.
If you are going for the exposure condition and durability, you will not go beyond that value. This table is
Yes,
that
ma'am.
one.
Yes, ma'am.
And that's why there also 10262 also it is mentioned that beyond this you will not go. That's
Yes,
why it
ma'am.
is minimum and your maximum. But that
Yes,
what is given, that one we have not discussed, no sir. Hurry. So that part is missed.
Yeah. No problem. No problem, ma'am. Thank you, ma'am.
Nice that for interaction session, and anybody also can join for interaction, not a problem. So we have a 8 minutes. Sir will join 7:30 because for them it is early morning 6 a.m. So we people may take a break or any other question. or any suggestion?
Hello.
Yes, sir.
Dr. Dada Patel again.
Okay.
Hello. No, but after the big season, whatever we do, I mean, again, we have to adjust here and there. I mean, sand always we have to increase, and so only this gives the guidelines. I mean, of course, this everyone knows.
Yeah, this is the guideline, and as per the
yeah.
designer
I mean,
only we have
yes,
to.
yes. Means
And
nothing I am
another
telling. I am not telling anything new, but just I want to reiterate that कभी भी क्या होता है हमको सैंड बढ़ाना पड़ता है थोड़ा वर्केबिलिटी के हिसाब से और कोर्स ग्रेड घटाना पड़ता है तो अपने को मिक्स से सिर्फ वाटर सीमेंट रेशियो और सीमेंट कंटेंट ही थोड़ा मिलता है बाकी तो थोड़ा एग्रीगेट में इधर उधर करना ही पड़ता है दैट इज व्हाट आई थिंक
सर वो डिपेंड करता है पर्सन टू पर्सन मिक्स डिजाइन
या
लेकिन वी
हाँ मिक्स डिजाइन से जो प्रोपोर्शन आता है वो कभी भी हम लैब में करेंगे ना तो वो कुछ ना कुछ प्रॉब्लम होता ही है मतलब जो एग्जैक्टली इफ यू गो थ्योरेटिकली तो मे बी आउट ऑफ 10 little bit here and there we have to do yes otherwise
and another important is IS 383 2016 that blended proportion also suppose nowadays our aggregate is coming too higher oversized aggregate so that blended proportion also people are doing that you can blended it the both fine and coarse aggregate for minimize the point and another is nowadays packing density is also coming for achieve the highest strength.
Yes,
sir. That is the reason why we are going for the trials for the concrete designs. Multiple trials. After multiple trials, only we can able to finalize the mixed proportion. Otherwise, not possible.
Yes, sir. Sir, and here another point is there. Whatever aggregates we do have during the design stage and trial mix will not be consistently getting at the site. Then whatever changes we get in the aggregates, then accordingly we need to make the adjustments because whatever sand and coarse aggregate will not be the falling too fast, no, to margins. Hello.
Yes, sir.
Muruma madam, if it is possible, please even have one FDP on
mixed design. What,
so
sir?
that the freshers who are there or who want to learn. Hello?
Mixed design. Yes, sir. Tell me. Yes, sir. You continue. Is it audible?
Hello.
Yes,
hello.
sir.
Can I share one more interesting thing in just 1 minute? Hello.
Yes, sir. You can continue.
Just 1 minute. No, what I heard from one of my friends that in USA, even what they do, they just create 3 conditions like summer, winter, and this one rainy season in lab itself, and they do not give any like in India. We पहले ही हम वो grade को announce कर देते कि मैं M50 कर रहा हूँ, M60 कर रहा हूँ. What they do, they just mix design करते हो, and then they simulate the condition of rainy season, winter end, and they try to see that same concrete how it behaves in different conditions, strength wise and durability wise. So that is also a good idea, which is I think I don't think whether it is coming here or not. Matlab, that is what it is really interesting.
Yes, sir. But in India we are not following.
Yes. So what he told was he did his post-graduation there. They had the facility that exactly they were simulating the condition of summer and they were not कुछ grade का नाम देते ही नहीं थे उनका सिर्फ ये था कि हम इतना सीमेंट यूज करेंगे and requirement only that there should not be segregation, there should not be bleeding, and the mix should be cohesive, and then they were not naming it as any grade or they were not following any rules of any code like that. Of course, I mean water content and all they were keeping whatever possible minimum. Economy was also consideration, and then they found that in different seasons, what is the strength it was giving and durability it was giving like that. So maybe that is more practical also, I think. Thank you.
Thank you very much, sir. Good evening, sir. Rishi, sir, have you joined?
Good evening, I'm here.
Okay, sir. Good evening. Welcome you, sir, in India.
Thank you. Thank you very much.
Soumya,
Welcome you, sir, in India. ಇವರೆಲ್ಲ ನೋಡಿ ಎಂತಿಂತವ್ರು NIT ದಾಗ
Soumya,
ಅದಾರ ಒಳ್ಳೆ.
please introduce.
Welcome
Yes,
you,
ma'am.
sir,
Am
in
I
India.
audible?
Yeah, Tuka.
Am I audible, ma'am?
Yes, yes, you are audible.
Good evening to the esteemed delegates, respected faculty members, and participants. It is an honor and a privilege to introduce our distinguished guest, Dr. Rishi Gupta, sir, who currently serves as a professor in the Department of Civil Engineering at the University of Victoria. Dr. Gupta completed his PhD in Civil Engineering at the University of British Columbia in 2008. His research focuses on developing sustainable construction technologies and innovative methods for infrastructure management. He also leads the Facility of Innovative Materials and Infrastructure Monitoring. In addition to his academic contribution, Dr. Gupta serves as a director of the Center for Advanced Materials and Related to Technologies and brings extensive administrative experience to his roles. Dr. Gupta is a Fellow of Engineers Canada, a Fellow of the Canadian Society of Senior Engineers, and a Fellow of the Canadian Society for Civil Engineering. In 2020, he was awarded UVIC's Reach Award for Excellence in Undergraduate Research Enriched Teaching. He was also a recipient of EGB's President's Teaching Award Excellence and UVIC's Faculty of Engineering Technique Excellency Award. With due respect, I now invite Honorable Dr. Rishi Gupta, sir, to kindly deliver his speech. Please, sir.
Thank you very much, Dr. Soumya, for the very kind introduction. And I hope I'm audible, not too loud, or the volume is good.
Good, sir.
Okay, that's great. So may I just share my screen and then we can begin. So just one more check. Everybody able to see the screen? All right.
Yes, sir, it is visible.
Perfect.
Visible,
Thank
sir.
you. Thank you
Thank
very much. So yeah, good evening, everybody, to all of
Sir,
you
good
in
morning also. Good morning to
yes,
you.
thank you very much. Yeah, it's 6 a.m. here in Victoria in Canada, but it's a great pleasure to join all of you. So namaskar and good evening to everybody joining us online. Um, I'm very excited to be here and just want to thank Dr. Meena right off the bat for thinking about me and inviting me for this faculty development week. I hear this is um last but one day. So this is Friday. I think you have one more session tomorrow on Saturday. So I saw
Yes,
the
sir.
agenda, look very, very good, very, very interesting topics. And when I was looking at the topics, I thought I slightly change what I had promised. So I'm not going to delete. In fact, I'm going to add something if time permits. So the title of my talk, as you all know, was Case Studies of Low Carbon Technologies in Canada. And I'll try and give some real examples of some technologies that I have been working on, I have been leading here in Canada. But in addition, I thought it may actually be of interest to talk about some of the projects that we're working on related to structural health monitoring, because this is always an interesting topic. So my introduction has been done already. The one part I will also mention, which may be of interest, is I'm currently serving as the Vice President International of the Canadian Society for Civil Engineering. And towards the end of my presentation, I want to talk a little bit about that as well. So with that, let's begin. And I just want to begin with what is the perception of Canada. So anybody not been to Canada before, what do we actually think of Canada? So of course, a few things come to mind. It came to my mind many years ago before I moved to Canada from India. And of course, we are thinking about igloos. We are thinking about polar bears and lot other things. But of course, Canada does have some very interesting civil engineering infrastructure, right? So everybody probably heard about the CN Tower at 1800 feet. And for those of you who've not heard about this, it's a very interesting project. The next one is the Confederation Bridge, which connects two provinces of Canada, and it's a 13-kilometer long bridge, an amazing feat of civil engineering. And I myself was attending a presentation on the Confederation Bridge where they said one of the most important design parameters for the Confederation Bridge was to design it to resist icebergs. So what would happen is in the wintertime, there would be chunks of icebergs that come across the bridge, and the impact of the iceberg on the piers was one of the most critical aspects of design. So of course, we have quite a few interesting structures in Canada to think about. Before I get into the technical side, I just thought I quickly place myself where I am sitting right now. So of course, I'm on the other side of the planet from where you are in India, and I'm in the province of British Columbia, so west, and I'm actually on an island. This is called Vancouver Island. But the small dot there at the bottom is where I am. So that's Victoria. Many people know Vancouver, but Vancouver is not the capital of British Columbia. Victoria is the capital of British Columbia. So I'm right at the south of tip of the island. Um, the analogy that I usually give, it's like sitting in Colaba in Mumbai. So the southernmost tip of the island there. Just moving along, today's topics, I thought I just, again, very quickly talk about my university, just one or two slides on it. I want to talk about what is the need for innovative materials, what is the need for sustainable construction technologies, and this is going to be sort of my interpretation on these two topics. And then we will jump into some case studies as promised. So we'll talk about pervious concrete or porous media, especially being used as flat work or being used as pavements, for example. We'll talk about my favorite rammed earth technology, and we'll also talk about a technology that I had privy to in terms of working both in research and in a company in Vancouver many years ago, which is a PVC, as we call it, SIP, stay in place concrete forming system. What I added here, as I said in the presentation, was the last part, some ongoing topics on non-destructive testing. I know it's a very hot topic, and structural health monitoring, but I just put down at the end, we'll keep an eye on time and see how much time we have for that little part. So just moving along. Very quickly, University of Victoria, also known as UVic. There's just a nice shot of University of Victoria. So we are here within a ring road. We have some ancillary buildings on the outside, but I like this photograph here because we are actually, like I mentioned, this is the southern tip of the island, and we look across the ocean. We actually see the US. So we are looking at a beautiful mountain here at the top called Mount Baker. And again, a nice view from the University of Victoria. We are about 20,000 students at University of Victoria. We have several different engineering programs. Of course, civil is one of them, but biomedical engineering, mechanical, electrical, computer engineering, software engineering is one more, which I don't have on the list, but these are some of the popular programs here. So with that introduction, let's continue to move on. Let's talk about need for innovative materials and sustainable construction technology. So why exactly do we need this? Of course, we are in a developed country here in Canada, but I just wanted to show you that some of the issues we have in Canada are actually quite similar to those in India as well. So this is a photograph. I still remember listening to the news in 2006, and it said one of the overpasses in Quebec has collapsed. So 5 people died in this, but this particular case study is actually very interesting because this particular overpass was actually inspected just a week prior, and it still failed afterwards. So this raised a lot of questions about how we actually inspect our structures, how we inspect our bridges. Of course, after that, the usual blame game, whether this was deficient structural design, or was it poor construction, or was it improper placement of rebar, or it was early deterioration owing to corrosion, or in this particular part, not so much for most of India, but for us, it's a big factor, which is freezing and thawing, right? So we have a lot of deterioration that can take place because of freezing and thawing. Of course, this particular region is in a very cold part of India. Another very quick example, Minneapolis Bridge. This was 1 year after Quebec Bridge. So this is, of course, in the US. Many more injuries here, many more fatalities. This particular bridge was commissioned in 1967. So it only lasted about 70 years. And we, of course, like to design our structures for much longer than that. The reason I put this bridge here is the Quebec Bridge that I showed you was a concrete overpass. This one is, of course, a composite structure with a steel substructure with a concrete deck on top. So a lot of issues here in Canada. And I just put this was a bridge in Rajasthan, in Kota, in India. And I think this particular bridge actually collapsed during construction. So, we have many issues happening in our world, lots of problems these days. Just to put some financial numbers here, these are very old. These are about 8-10 years old. But I can tell you that these numbers have only gone worse because we are not investing as much in our infrastructure. And I talk both about Canada and India. I think there's a lot of infrastructure deficit that we need to fix. The last one here at the bottom is actually very interesting, because sometimes when we talk about uh, all of the infrastructure, it becomes very difficult to relate about the issue, because in some of these numbers, when we talk about general infrastructure, everything is included. Your water pipelines, your sewers, your airports, and all of that. But like I said, my favorite is the last one. If you look at infrastructure deficit in Canada, so just for bridges, fixing just bridges alone, the deficit at about 10 years ago was $8 billion. And I know that that number has only gone up since then. So huge problem for us to fix. This again, like I said, this is about 10 years old. India, the then finance minister, Mr. Chitambram, actually had put down a 1 trillion deficit for India in terms of fixing the infrastructure. Now, just moving along, what is the solution? Well, how do we fix these? We of course have to manage our infrastructure. And when I was thinking about this, I just thought about different aspects. And again, this is my interpretation. This is not coming from a textbook or anything. I think to manage our infrastructure to move forward, we need sustainable technologies. We need sustainable materials. We need sustainable composites. Composites is a big future. I think it's already here. Many of our structures, many of our systems are being designed by composites, whether it be cement-based composites or be polymer-based composites. That is already here, owing to the many benefits that we have from composites. We, of course, have lots of existing infrastructure. We cannot just bulldoze everything down. We have to think about how we can extract a safe life from the existing infrastructure. And for that, one of the key aspects is condition assessment. We need to know what's the condition of that infrastructure right now. I think sensors will play a very important role here moving forward, both for new construction and for existing structures. And I think this is already happening, but I think at a very, very slow pace, both actually in Canada and in India. And just life cycle assessment, I think will play an important role. And finally, structural health monitoring, both, like I said, for new and repaired structures will be an important part. So these are just some my sort of reflections on infrastructure management. These are my reflections. This is what we focus on in our research lab at the University of Victoria. So moving along, some sustainable construction technologies. So not just materials, but we of course have to think about the entire technology. What's the carbon footprint of how we construct these structures? How long are they going to last? So we have to look at the full picture. And like I mentioned at the start, I'm going to talk about 3 case studies with you. We'll begin with the first one. We'll talk about pervious concrete here. Maybe for pervious concrete, I'll start with the problem statement. So what you have here, actually, you see the photograph at the bottom left. That's the photograph I took I was in Vancouver. I used to live in Vancouver before, and I took a photo right from my house. I'm standing in front of my door and taking a photo at the street. And of course, you see my little garden there with some ice or snow in it. And you can't see it, but in my garden, I have some tulips growing there at the bottom here. And that reminds me that if I have tulips and if I have a little bit of snow, this is probably about end of March or the month of April. But the reason I put this photograph here is, of course, Vancouver gets a lot of rain. Vancouver gets about 1,000 millimeters of rain every year. And what you see in front of my house is we, of course, have the paved asphalt road, but there's a very broad shoulder. So I don't know if you can actually see my mouse or not, but we have the shoulder here. And then the little stream of water that you see is actually the sidewalk. So this is where people would be walking or would be expected to, people either biking or wheelchairs or whatever. But on this particular rain event, we have a pretty large amount of water flowing into the stormwater drain here. But in addition, what's interesting is the quality of the stormwater. So what we have done in trying to modernize our infrastructure is we of course love paved surfaces. Nobody likes to walk on soil or dirt, and we like to either put compacted gravel, or we like to put asphalt, or we like to put concrete. So what we're doing is any pervious surfaces that we used to have in the past, we're trying to make it paved surface. Of course, the problem with the paved surface is that it does not have it's not as permeable as having grass, for example, right? So water would fall on it and would go right through it. But paved surfaces, we are generating more runoff than actually we can handle. So what you have here is we have increased runoff, poor quality, and again, you can't see it here on the photograph on the right-hand side, but this is a very large parking lot, and we have runoff coming. And rather than the runoff going into the grassy patch, we are diverting all of that into the stormwater system, right? So this is becoming a major problem as we move forward, and we'll talk more about this. So there are different solutions to stormwater management. The solution that I'm presenting is coming from a materials angle, not from hydraulics point of view. And one of the solutions is that if the infiltration on the parking lots and pavements could be increased, however we do it, and there are different techniques to do it. The one that we were focusing on was going to be by using pervious concrete. So let's move forward. And what we have here is pervious concrete. So very, very quickly, so these are some of the samples we were investigating. And pervious concrete, also known as porous concrete sometimes, sometimes known as no fines concrete. Um, um, Porous concrete or pervious concrete, of course, has lots of voids. If you look in literature, pervious concrete can have anything from maybe 5% of air voids all the way to 40%, 50% of all air voids. The systems that you're looking at, little briquettes that you see in the image, were roughly give and take in about the 25 to 30% air voids range. Now, just a side sustainability angle with pervious concrete is because I have 30-40% air voids. Of course, there's a sustainability angle. So it of course becomes lightweight. That's a side advantage that we have. And of course, for the same volume of the materials, we have 30-40% more material because we have voids. We filled it up with more. So just we'll keep that in mind as a secondary benefit. But why were we doing this? So there's a lot of work that's been done on pervious concrete or porous concrete. The reason why we were looking at this is, according to me, porous concrete is not a solution for every place. And porous concrete has to be thought about depending on the site. So if the subgrade or the soil underneath does not have the capacity to percolate water, then there's no point having the media at the top, which is porous. So we have to think about site-specific conditions and decide on the percolation capacity of the media depending on what the ground can actually absorb. One of the big problems, and I keep hearing this in India as well, that clogging of the voids, right? So I start with a system with 30% voids. I'm going to have contaminated water with lots of sediment load flowing through the porous concrete. And of course, the voids will start clogging over a period of time. So the question was, how long can porous concrete last? Abrasion resistance. So you saw in the photograph before that I had here. Looks like very gravel. This is also because there are no fines to hold the aggregates together. The aggregates can dislodge, and I'll talk a little bit more about that. So the abrasion, the dislodging of the aggregates can be large, and we wanted to know how large that will be. So let's talk about our case study here. So I say this in a funny way. This site was located in, sometimes we laugh and say it's not Vancouver, it's Raincouver. because we get more than 1,000 millimeters of rain every year. We almost have 7, 8, 9 months of precipitation happening here in Vancouver. Victoria, where I am now, is also similar. We get slightly less rain here, but it's a very similar weather pattern. So what you're looking at is an aerial view of a parking lot. Of course, this is all paved, full of asphalt, but you can have an appreciation of the size of this parking lot. So imagine this being unpaved, being green many years ago. But of course, we need parking lots, so we've made it into a parking lot. Uh, at this location, there were 5 of these parking lots. So you can imagine the amount of stormwater that we're going to generate from almost impermeable surfaces. What made this interesting was just on, you see the west side of these parking lots, there is a creek and called Gishan Creek, and it is inhabited by a fish called salmon, as you may have heard about. So all of this parking lot, what is the issue here? That the issue is not only are we generating stormwater, but if the stormwater did not go into the stormwater drains from all these vehicles, from all the asphalt, the stormwater is going to have very high hydrocarbons in it, and that can be pretty brutal for some of the water bodies. So what we did was we looked at this very large site. We looked at one of the downstream locations. So all the flow was taking from the east to the west, sort of from the south to the north. So this would become a place where much of the stormwater would pass. So we picked that site, and we picked 3 stalls, and I'll show you more. The reason why we picked these stalls was we wanted to use porous media as mainstream paving material. So not for so small sidewalks, not for walkways. We wanted to see how porous concrete would perform in as a part of a pavement, as a part of a parking lot, for example, where we have moving traffic. So the reason we picked this location was we would get moving traffic, so traffic going straight across. We would have standing traffic, so the people in transportation would know that sometimes standing traffic can actually be more stressful for the pavement than simply moving traffic. And of course, what we would have here is the traffic would be turning, and what happens is when the wheels and the tires are turning, they actually induce way more stresses at that localized region for the pavement. So this is what was of interest. Just some nice photographs here for you to appreciate. So what we ended up doing was we cut down 12 inches of the pavement. So the asphalt was at the top. We cut down about 12 inches. The subgrade was compacted with clear crush. So this is simply gravel or aggregates. And so that was the sort of the base of the concrete. And then the construction process began. And I just want to show you something very interesting. So when we were doing this project, this was new to me. And what ends up happening with porous concrete is you do not want to compact it too much. If you compact it too much, of course, your voids will be reduced that you designed it for. If you compact it too less, of course, your strength keeps going down. The strength of porous concrete, as you may imagine, is already lower, right? So you just need the right balance of compaction. What's happening here is very interesting. What's happening at the top photograph here, this is a very large roller screed. So it's actually like a pipe, and there are ways to close the 2 ends of the pipe. There are 2 handles here. So this gentleman is holding a handle here. There's another handle at the bottom, and there's actually a switch. So the whole entire tube actually rotates while 2 people can pull it across it. In addition to that, the tube can be filled up with water, or you can add sand or whatever inside and seal it from the 2 sides to increase the weight. So you have vertical compaction just by the dead weight of the screed, but it's rolling. So you're actually doing compaction and finishing in one single operation. So this was very interesting. I'd never seen this before. And what's happening here is a little manual screed at the bottom to get the fine finish that you desire. So very interesting process, was actually very quick. Curing took place as would be expected here. And this is the finished placement. So we have the 6 inch of gravel at the bottom and roughly about 6 inches of concrete at the top. Very interesting, of course, to see that the porous concrete looks actually like compacted gravel, but of course the cement binder is there to hold it together. This is a finished, so I'm standing at that location looking up. One of the interesting parts was this was coincidental. We didn't plan for this. That the color of the porous concrete was actually very similar to that of the rest of asphalt. So it actually did not stand out. Actually looked pretty good. On porous concrete, just some ongoing work, which was not a part of this project, but was absolutely of interest to us, was hydrological, environmental, and the structural properties or the material properties. So I'll just give you a glimpse of what I'm talking about. I won't get into the details here, just keeping an eye on time. So what we did in our porous concrete test patch was we had perforated pipes. So these white pipes that you see are perforated pipes, and this is sitting just over the sub base, and the porous concrete would come on top. So these are embedded inside. And what we wanted to see was how much water actually infiltrates through the top surface and how much. So we were trying to measure it on the downstream side of these black pipes to see how much water percolates through the top portion of the porous concrete, how much water percolates through the subbase, so that we can actually develop a profile and estimate how much water can actually be absorbed by the pavements. So some of the percolation numbers. So you see 60,000 millimeters an hour. So these were measured. I think I had the photograph here. So these are ASTM tests. So what you do is you put a ring, you pour water in it at a prescribed rate, and you measure how much water is percolating through it over a period of time. And what you can actually do is you can calculate the percolation capacity of the porous concrete. So we started off with a very, very high percolation capacity. I don't think we needed that much percolation capacity, but it ended up giving us a little bit of a buffer because we knew that the percolation capacity will reduce over a period of time due to the stormwater contaminants that come with it. Just a visual here at the bottom. So remember I said the percolation, the spot was on the downstream side. You see a lot of rainwater is coming from the upstream. It hits the porous concrete patch, and by the time it crosses about 3/4 of the test pavement, everything is actually absorbed within the stormwater. So that was a very good sort of a visual that we had, that our technology here was indeed working. For those who are on the environmental side, of course, when I showed you the photograph, I'll just please excuse me, I'm going to go back to this photograph, which I like a lot on the left-hand side. Whenever I see something like this, it actually reminds me, I don't know what it reminds you of, but it reminds me of a filter. So you know, a classic example of a sand filter where you pour water, and by the time it goes down, it becomes the contaminants are removed, and it actually the quality improves. So when I look at this, that's what it reminds me of, and that's what we were trying to do here, to see if the aggregates and the spaces between them actually have the capacity to reduce any of the contaminants. So biological oxygen demand, for example, chemical oxygen demand, and so on. Before I started, I know there was some discussion happening on concrete and durability and all of that. So just to put this out there, the cylinder that we are holding in our hand, of course, looks very nice. It looks like porous concrete. If somebody was doing regular concrete, they would say that's very bad concrete. It has lots of void, poor compaction. But in porous concrete, that actually looks very, very nice. Good distribution of aggregates. Our density had gone down from 2,300 to about 1,700 kilos per cubic meter. Our strength was, of course, as expected, was dramatically down, right? So we were down maybe 3-4 MPa of concrete, but that's the reason why we had 6 inches of concrete. And I may present one of the potential research areas here is one of the reasons that contributed also to the poor strength of concrete is there were no standards that prescribed how to make cylinders for porous concrete, right? So I know in India we do cubes. There is a standard procedure to make cubes, how to compact them. We have similar in Canadian Standard Association and ASTM prescribing how to make cylinders. But how to make cylinders for porous concrete? You cannot do tamping with a rod and so on. So I think part of that was that. If I had to guess, I think we were more like 10 MPa, which is what our industry partner had actually targeted in this particular case. Just trying to finish the first case study here. I mentioned about abrasion, the word that's actually used for porous concrete. The word actually is called raveling. And what that means is basically dislodging of the aggregates from the top surface. So if you recall, I had mentioned that we had strategically picked this spot. So we get the effect of standing traffic, we get the effect of moving traffic across the pavement, and we get the effect of turning traffic because they're trying to go onto the other side into the second parking lot. So we were monitoring that. And again, that was sort of my last part to say that the overall performance of the porous concrete was good. We were able to demonstrate that porous concrete can be used as mainstream pavement, but of course there are still lots of unanswered questions from that case study. So with that, I'm keeping an eye on time. So that's about 30 minutes for the introduction and the case study. I think we'll move a little bit faster now. So the second case study, this is again an ongoing project. So this is a zoomed in view. So I'm going to take you from Vancouver or Richmond right here from mainland, and I'm going to take you to our island to Victoria. So this is again our ring road, University of Victoria Ring Road. And what we have is we have a test site on campus. And I'll explain more about what's called the HAL site in a few minutes. But I just want to start with a general introduction of LIDs. I'm sure many of you have heard about low impact developments or LIDs. There are different interventions for LIDs. We have green roofs, bioretention cells, rainwater gardens, swales, and of course permeable pavements, as you've mentioned. But what we are doing generally is we have these low impact developments. So there's stormwater runoff. We have a low impact development, and that's where we stop. What we were thinking is, what if we could come up with almost a treatment train in series, where we have a combination of not just one technique, but more than one technique. So how would that look like? This led to us starting about 10 years ago, I, along with my colleague, Dr. Katrina Vallejo, an idea of having, like I said, two interventions in a row, and that's why we call it hybrid absorbable landscape. And I'll show you examples of this in a minute. But we're not relying on just one technology, but we are actually relying on two technologies to perhaps improve the quality. Again, the focus is going to be on stormwater management here. So our test site, what we have, this is a plan view. So looking top down on the schematic. And again, I'm going to show you some photographs. Our test site is again placed right in the middle of an asphalt parking lot. Again, same issues, lots of stormwater being generated. But what we wanted to do here was, let's just look at the top part of this image. So this is all asphalt, lots of water being generated. Our idea was, the first intervention we would have is we would force the stormwater to go over a permeable media. On this test site, we actually play around with this. We remove the test patch, we put something else depending on what our industry wants to have. There are 3 or 4 technologies here. There is a technology for stormwater permeation called grass grids. These are just plastic grids. Traffic can drive over it, but it has lots of percolation. So that's here. I'll show you a photograph later on. Porous pave is a product made from 100% recycle, not 100%, 50% gravel, and 50% recycled tire waste combined together with a resin. And again, it has a lot of infiltration capacity. So we had that. We had porous asphalt. Eventually, we even tried porous concrete on the side. Very popular for India is pavers, right? So we have concrete blocks or concrete pavers. They also have infiltration capacity if you do not put a PCC course at the bottom, right? If you put a PCC course, of course, it's not going to absorb anything through the PCC layer. So the idea here would be divert the stormwater, take it through front end porous media, let it soak through the porous media, but don't stop at that. Then at the bottom, by having a membrane, allow or force the water to go from the porous media into something else. So what you see in the middle, these are bioretention cells. And what is in the bioretention cells is my colleague, Dr. Katrina, focuses on what can plant species or trees do to remove contaminants. So these would be three different varieties of plants. We are looking at some native plant species, which actually have very good uptake of water. So when they take a lot of water, they also take a lot of contaminants, and they would actually help clear or reduce the contaminants in stormwater. So the reason this is called a hybrid absorbable landscape is we are using two interventions, porous media here, along with a bioretention cell in tandem. The one question does come up later on, which I will answer right now, is, of course, if the stormwater is more and our media does not have the capacity to handle it, where will the overflow go? So this is not an isolated system. Eventually, from the bioretention cell, the water would go back into the stormwater drains. But what we've done in between is, with our intervention, tried to improve the quality. And if I may mention here, that we've also done is slow down the flow of stormwater. So by this, we have retained the water, and that's actually very good for sort of cutting down on peaks and lows of stormwater flow. So just moving along, I'll show you some construction photos. So these are those 4 bioretention cells I was talking about. The bioretention cells here, because we have an academic research purpose, we actually line them. So we wanted to see what individual trees are able to do for us. So we know exactly what contaminants are coming into each bioretention cell, what the trees are able to do. So this was during the construction phase. And then this is what I was talking about when I mentioned about porous pave. So these are our test slabs, but this is how the one on the top right looks like. The finished surface looks actually very nice. This is a close-up view of porous pave. And like I mentioned, it's a resin-based binder, but it has recycled tire, rubber, and it has gravel including. So very high percolation capacity. I don't know if you can see this clearly, but these are the grass grids. So you just lay them, fill them with soil. So that was the other technology. This is porous asphalt that we laid down on the construction site. And all of these are of interest, by the way, to not just the industry partners, but these are very much of interest to the municipalities, because at the end of the day, the municipalities are the ones who would have to deal with all the stormwater that's coming to them. Again, so just a before and after. This is how, so aerial view, this is what the little patch looked like before we intervened, and by the time we finished, this is how it looks like. This is very initial stages of the project. Some of the trees have actually grown quite nicely here, so it actually looks like a nice working site here. So just some photographs of our team. I may not have time for this, but you see the little hut here in our background. That little hut actually has the data acquisition system for monitoring. So all the white pipes that you see sticking out here, they have different sensors for water quality testing, and the little hut here actually stores all the data from this test. So again, just these were some photographs that I wanted to mention about health monitoring. So we have our own Met station here, because as you may have heard, the microclimate at a site can be very different from everywhere else. So we are trying to monitor that as well. I won't, just keeping an eye on time, maybe I won't spend too much time on the data, but of course, like we did in Vancouver on our porous concrete, the idea is we do want to measure the infiltration capacity. In many of these systems, the infiltration capacity will go down over a period of time. So I won't spend time on the slides, but just to show you, we did have infiltration capacity actually that went up a little bit, but then it started coming down. And just some final remarks here that the hybrid absorbable landscape can actually be a very good potential. You can use any combinations depending on your site, and I think it can be a very good way of managing our stormwater moving forward. So 2 case studies done. I have the third one, and I have health monitoring if possible. So let's begin with our third one. And this third one is, of course, on rammed earth, which is also known as cement stabilized soil. I do want to mention that actually there is a lot of work happening. This is a very, very hot topic. There's already a lot of work happening. I know in India, and I know in eastern parts of India, there is, in fact, northeast parts of India, there is a lot of work happening on rammed earth as well. And I will present you the Canadian perspective on rammed earth, and I'll showcase some of the work that we have been doing here. So the motivation here for rammed earth, I am not sure how many of you have heard about this. There used to be a thing called 100-mile diet, and this particular diet would say that if we wanted truly to be sustainable, we actually should be eating what's available within 100-mile. I don't know if they said a radius or a diameter, but let's call it a 100-mile radius. So anything that you have within a 100-mile radius, that's what you consume if you truly want it to be sustainable. So if I'm sitting here in Victoria in 0-degree temperature, and I want to eat watermelons, there are no watermelons within a 100-mile radius of where I am, right? So the idea being that what I'm eating is coming from longer distances, and that's not sustainable. So the same motivation goes for construction in general, that use local, right? So and again, I give examples of India because I, of course, learn a lot of things from India myself, where if you have bamboo in locally available, is there a possibility to use bamboo for construction, for example? Or if I have desert sand available in western parts of India, can I use that for construction, right? So something which is local is the idea. I give you an example of Tibet here. So what's happening here on the left-hand side is the entire village comes together, and they decide to construct one house or one structure at a time. So it's a community effort. Everybody comes together. You can see in the photograph, it's basically just soil that's being used, locally available soil. The photograph on the right-hand side, you can see all the people are standing on the walls, and they all have, not everybody, but many of them have hammers with them. So they're basically compacting the earth. If you look a little bit closely at the opening or the windows, you will see the cross section of the wall. So I'm talking about here. If you see my mouse, and if you see here, and what you can see is that the thickness of the wall is very large. And the reason for this is in certain weathers and climates, you can actually make use of the thermal mass of the structure to offset the variations of climate outside. So become too cold, too hot, but your nice mass of earth can help keep the temperature inside a little bit more constant. So that's what is the traditional way. There are lots of different structures constructed with rammed earth. Lots of examples from Iran to China to in India as well. So this is, I will call it the traditional way of doing rammed earth. This is how the constructed house looks like here. But what I'm going to present to you is what I like to call the modern way of doing rammed earth. The biggest difference here with the modern structures that I'm showing you and what I showed you in Tibet is in the structures in Tibet would be just soil. So they may have some grading taking place between soil, maybe some clay to bind things together and so on. But the applications I'm talking about, the traditional form of rammed earth would not stand here because remember what I said, 1100, 1000 millimeters per year of precipitation. So for wetter climates, the traditional rammed earth would not stand. So what they do here in Canada, or at least the parts I am in, is they actually it's cement stabilized soil, right? So it is the rammed earth technique of construction, but in the material we've used cement to stabilize it. It's still a very dry form of the material that's actually used for construction. And two structures here. So this is a beautiful garden here in Vancouver called Van Dusen Garden. So you enter the garden and you look at the structure. It just looks very, very beautiful. This is again a house constructed on Salt Spring Island, very close to where I am. And again, the house looks very good. Not in the top photograph, but in the house, I must mention that rammed earth for residential purposes or where we have inhabitants, one other difference would be that they would actually make them insulated walls. And I'll show you a photograph eventually. But what's happening here is you have two sections of rammed earth with an insulation sandwiched in between. So now you're trying to get the best of the thermal mass, and you're also trying to get the insulation from the walls. This is on the island. This is the photograph I took a couple of years ago. This is like a community washroom that's constructed. But you look at the wall, they have accentuated the layers by adding pigments in different layers. And I'll also talk about how the rammed earth is actually constructed, and that's the reason why you get this beautiful layers that you see in concrete. So again, another shot here, just very magnificent looking buildings here. Now let's talk about the construction. How are those constructed? So this is happening in my labs, and what we're trying to do is I'll explain the motivation. Of course, with rammed earth, there is a big design question. The structural designers are asking if rammed earth should be designed as a concrete structure or rammed earth should be designed as a masonry structure. The reason why they're asking these questions is remember, rammed earth is a very dry mix that we're using in construction. So the bonding of the earth with rebar is not going to be the same as traditional concrete. So a few things about rammed earth is, of course, the cement content can be lower because the water cement ratio can be lower. We don't require the mix to be flowing. It's very, very dry. The mixing is taking place in traditional mixers. And then what we're doing is, as opposed to the traditional form that I showed you in Tibet, where multiple people have hammers and you're manually doing this, what we do is there's a pneumatic hammer. So you can see my industry partner here holding this pneumatic hammer. So what Mirror has in his hand at the bottom is it's basically like a piston. And what you do is you feed the end of the piston to a pneumatic compressor. So I can roughly have about 4 compressors running at the same time. And what all he does is just holds the pneumatic hammer. And when you turn it on, the bottom just goes like a piston, like an engine, goes cup, 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 cup. And of course, the productivity goes up a big time because now you don't have to manually move it. All you're doing is just moving the hammer around. Again, the same thing is happening here. These are 2 separate projects, actually. This was in Vancouver when I was in Vancouver. This one is actually happening in Victoria. And again, I'll show you some nice photographs. We were trying to answer some of the design questions. In fact, some of the work that we did here in the top photograph led to the designer constructing the wall that I showed you before, which is the Van Dusen garden wall. So they use some of our test results to construct that. Okay, so back to rammed earth. We had some research questions here that we were trying to answer. Formwork pressure, for example. So as if some of you are in the design of formwork, you know that there's traditional concrete, but self-consolidating concrete is one of the major design issues in design of formwork because the pressure is very, very high. The same question was for rammed earth. So now I'm consolidating vertically using a pneumatic rammer, but what's the pressure on the forms? If it's a dry mix, is it zero? But if I continue to compact, what would be the lateral pressure on the formwork? So that was the question that was being asked. So we're trying to install some lateral sensors here, pressure sensors, to find that out. The two photographs that you see in the middle here were sort of the big design questions. So the structural designer wanted to find out if stirrups or loops in the column versus diagonal, which one would perform better in terms of the performance of a rammed earth wall. So of course, rammed earth, we are thinking about vertical wall construction. This is a nice photograph, actually. It shows you the insulation in the center, right? And rammed earth would be on the two sides. So again, here's the rammed earth with the stirrup and insulation. Both types of shear reinforcement have their own issues because you have to cut through the insulation to go across. So our structural designer partner was very interested in finding out solution. Here are some sort of a top-down photograph. You're trying to find out what's the bond of the rebar when rammed earth is placed across the rebar. Of course, in this situation would be different. Rammed earth would be going around the rebar, different bond. We were trying to find out in the bottom right photograph, what's the wetting and drying effect. So I have different cycles of wetting and drying. What would happen to the rammed earth long-term durability? This is a small little wall, mock wall that we constructed using rammed earth. And we looked at long-term deterioration of it using some non-destructive test method. So very, very interesting. This is an 8-foot wall, I think, if I remember correctly, a full-scale wall that was constructed. You can see the beautiful layers here. And some of you may be wondering how these layers are formed. So what ends up happening in rammed earth is you construct your forms. You put down about 6 to 8 inches of material in the forms, which of course you cannot see. And then you compact it down to bring it to roughly 4 inches, 3 to 4 inches of layer. But of course, you can't see it in the form. Then you go with the next layer, you put about 6 to 8 inches of fresh material and compact it down. So you never know what's happening in the form. But fortunately, in this case, when you strip it, just the natural texture, it just looks amazing. So there are a lot of people trying to use rammed earth to blend with nature, right? So if you use local soil and you construct your structures, of course, you're going to blend well with your native environment because it is native material and it does have a little bit of a natural sedimentary rock look here. So this is showing you full scale wall testing. So if you can't figure this out, this is insulation in the middle, 2 rammed earth sections on the 2 sides. So that's the sandwich wall cross section. We just painted it white because we wanted to see where cracking was taking place. And here's a load cell. And we are applying a lateral load. So we were trying to find out what's the out of plane bending strength. Just keeping an eye on time here as well. We will move forward. So again, remember the 2 design questions, diagonal shear versus stirrups. And the end of the day, the performance for the structural designer was the inclined stirrup wall performed way, way better than just having the stirrups in here. And that's what the designer took for future design considerations. So a very interesting project. We continue to do a lot of rammed earth construction. If you are interested, please just look up do rammed earth in British Columbia, and you'll actually see lots of beautiful structures being constructed. So we'll move on to before health monitoring, my last case study. And this is a PVC stain place concrete forming system. In India, I think the insulated construction is catching up. In Canada, it's been here for a very long time. For those who have interest in insulation, you may have heard about, or you can search it. It's called ICF, insulated concrete forms. And the idea with ICF is you have insulation on the two sides, and you basically place concrete in the middle. The two insulation pieces of the formwork, you just leave them in place. So that's called insulated concrete. What I'm presenting to you here is actually quite different. Here the insulation is in the middle, not on the two sides. So just very quickly, I do want to mention, so this comes from my time when I used to work for a Vancouver-based company called Octaform Systems. And I got a lot of information and a lot of case studies that I can share with you because of my interaction there. So basically, what the company manufactures is they manufacture PVC panels along with connectors. So you see this person actually, there are all these panels which have been laid already. And this person is actually right now sliding connectors inside. So there are panels, they slide connectors, and panels go from the other end as well. So what ends up happening is you basically create a box, like an empty box of PVC panel on one side, PVC panel on the other side, and connectors in between, and fill it up with concrete. And insulation also goes in the middle. And by the time you're done, you don't strip the form. The form stays there, so it becomes a stay in place form. What's different here from ICF is that you would have a finished surface of PVC. And I'll show you, there are some applications for PVC finished walls, whether it be in restaurants where it's very easy to clean it, or car washing sites where it's much difficult to clean up concrete walls. It's much easier to actually clean up concrete walls with PVC on it. And so just changing the alarm here. It's going to sound. Sorry about that. Yeah, so that's what we're looking at. This is a top-down view of connectors. So this is in our research lab. We wanted to look at what's the benefit of the PVC encasement on the structural properties of reinforced concrete. So you can see in the back here, actually, this is a very large, very tall wall, right? Like 15, 16 feet of wall. This, of course, would be reinforced as well. In terms of applications that I mentioned to you, the system has been used for residential construction, commercial construction, car washes. It actually has been also used for very large tanks. So you see this gentleman is actually working on a tank right now, and you see how the curvature can be had on the form because it's a flexible plastic. So lots of interesting applications. But what the company was looking to do was to look at what's the effect of the PVC in addition to just being a forming system. Does it actually do anything else other than that? So this is the top view. There are different configurations of panels and connectors that the company has, and they were interested in seeing what's the contribution of each one of this for actually on the structural strength. So again, this is a top-down view. We are looking down at the hollow of a wall. So here we are in our lab. What we're doing is we brought a ready mix truck. It's backed in. And what you can see here is three different heights of columns. So we have short columns, medium columns, we have some tall columns. If we wanted to see the effect of buckling and so on taking place. And here is compaction taking place with a needle penetrator. The crew from the company is doing that. And then we were testing our columns again in pure axial load. So this would be one piece of the wall, right? So one cell of the wall, this would continue. But of course, testing a wall can be a little bit difficult. So we were looking at one little cell at a time. I won't get into the details of all of this here, but of course, what we were trying to do was we were trying different heights of columns. We were trying to compare it to control, of course. So this is relative to control. So if control had whatever value, we normalized it, and we're looking at percentage increase. And what was very interesting here, and we spent a lot of time trying to come up with a hypothesis about why this would be the case. Honestly, it still remains a little bit of a sort of lack of research that we still need to figure out. But other than one system here, which is shown in red in configuration 4, all other systems showed an increase in the compressive strength from as compared to control. So this was very, very exciting news for, of course, our industry partner, because not only was the forming system doing forming, but now it was for some reason was actually helping in contributing to strength as well. Of course, the first thing that comes to mind is confinement. So confinement will help you increase the compressive strength. But remember, this is not a very high modulus material. We're talking about PVC, right? So again, there were a lot of different things. I'll just throw one other idea. One of the hypotheses was because it is nicely encased, the curing of the concrete is much better because the moisture is contained inside the PVC. Just as a secondary benefit, I wanted to mention, so here's a completely tested column, right? So you have, of course, from crushing of column to, sections being lost during compression. And next to it is a PVC encased column. This has also been tested, but as you can see, everything is, of course, still contained within. So I know I'm talking to technical people here in the domain. So when I look at this, probably lots of applications come in mind, whether it be for seismic purposes, for example. There have been interests for blast purposes for this as well. So lots of interesting stuff. Just to follow along on the same PVC encased system. So we looked at compression right now. There was also the question that was raised that compression is fine, but of course the PVC system is used for walls. So how about the effect of the PVC in bending, out of plane bending, for example? So now I take you very quickly from Victoria just to the south of the border. So we are going to Seattle University, and this is where we were interacting for this particular project. Some of these are published work. So if anybody had interest in some of these case studies, of course, you can look them up, or I'll give you my email address. You can contact me. I'm happy to share some of this published work for many of the case studies that I've presented today. So I'll sort of maybe speed up a few things here. It's I think 8:35 your time. So we'll keep an eye on that. So what is the effect of the PVC forming system on the mechanical properties of concrete? So of course, we always like to start with compression. So we did that. But in addition, what was different now was we made beams out of it. And what we have is we have traditional reinforcement in it. But in addition, of course, what we have at the bottom would be the PVC layer, right? So here is again some very interesting visual conclusions for you. Here is a cube tested. Of course, the reason why we had to switch to cubes here was we wouldn't be able to make cylinders out of PVC forming system. So we made cubes, and you can see, as would be expected in the compression, a lot of material loss. Same thing here. The concrete has crushed already, but it's still contained within the plastic. This beam, you can't actually see the panel, but the panel would be at the bottom. And what would be on the face that you see right now, that actually would be the connector. So the hollow connector. And looking at the flexural capacity of it. And again, we looked at different configurations. If you just focus our efforts on the second figure here at the bottom. You can see configuration 1, 2, 3, and 4, and you can see the control beam in blue performs the way we would expect a reinforced concrete beam to perform. But again, surprisingly, all the configuration that we had in PVC had superior performance as compared to the control beam. So again, this was a very good finding. I won't get into too much of the details here, but again, tested beams still contained between the PVC. We, of course, did our standard Whitney block and all of those calculations to quantify. Like I said, this is published work. Happy to share it with you. And I know it's getting too late in the evening for all of you, so I don't want to bore you with too much of heavy material here. So we'll keep moving forward and sort of come to the last part, which I added on for the presentation today, which was structural health monitoring and non-destructive testing. And before I get into it, just very quickly want to mention that of course, we can come up with new technologies, new breakthrough, but our clients, our industry, and our codes and standards will eventually ask us that show us evidence that your new technology is doing what it's doing. And in my opinion, health monitoring and non-destructive testing are a couple of ways to show evidence that the new technology that we have created as engineers actually does its job. So let me get into this. Some of the projects. So again, I'm just trying to give you a very high level glimpse here of some of the projects that I have been involved in. Some date back almost 15 years ago. So in fact, this particular one on the right hand side top was during my days in Vancouver at the University of British Columbia. And what we're trying to do here is these are embedded sensors. So these days, embedded sensors as concrete seems like sort of a routine thing. But if you can imagine about 15 or 16 years ago, this was relatively new. So what we're trying to do here is we do have two placements. We have control concrete and we have a fiber reinforced concrete pavement. This particular fiber reinforced concrete pavement had cellulose fibers in it. And we wanted to compare the performance of the two pavements to see how they're doing. Of course, we could do non-destructive testing, but we were actually in this particular situation interested in the early age behavior. So what happens within the first 3 or 5 days? So we had embedded sensors. So that's one example that I wanted to show you. Let me do the bottom right first. That's where I am trying to help out with placement of some of the sensors. This was one of our first projects where we use not just embedded electrical sensors. And again, this goes back about 15 years, was the very first use of embedded optical sensors that we use for shrinkage measurement. The one on the left-hand side was actually a joint project between India and Canada. And this particular one was doing condition assessment using drones. And we see my partner in crime, Dr. Bala here in the background, who was visiting University of Victoria a few years ago for this particular project. So this just gives you a sense of some of the different projects that we've completed. I wanted to give you a last glimpse on an ongoing project that we're working on right now. Remember the view to the Mount Baker on south of the border in the US. So again, this is a view from a local reservoir that we have here. The mountain is called Mount Tolmi. And what we have on the top of the mountain is a water reservoir. And I'm standing on the water reservoir while I'm taking this photograph. And what we have is, I think, an issue which is very common, again, between Canada and India. We've got lots of infrastructure that's aging, whether it be dams or water or whatever it may be. This particular water reservoir was constructed in the 60s. There was some seismic retrofitting done in the 90s. Remember where I am in Victoria and Vancouver, we are on the western belt, and we are expecting a major earthquake anytime, right? So we are in a very active earthquake zone. And this has about, it's fairly large, 4.8 million liters of water in it. So the municipality came to us and said, yes, we have this huge water reservoir on top of the mountain, and we are not sure what we should do with this. Should we decommission this? Is it safe to continue for some more years? If a seismic event takes place, how will we know whether anything has changed? Is it still good to go or not? So we looked at this and we said, yes, we can help you with that. And again, I'll try and give you just some very quick glimpses here. Dr. Meena, I hope another 5-7 minutes is fine for the presentation.
Yes, sir. No problem. No
Okay.
problem, sir.
That's so just our team here from Scott from District of Saanich, and we had our active student team here. Karthik was actually a visiting student from India at that time, and he had come to visit us on a My Tax grant. So we worked on this. I'll skip this part and go into the non-destructive evaluation part. So what we did first was we went onto the structure. And of course, anything, our basic test, of course, starts with a Schmidt hammer, because we didn't even know what the rough strength of the concrete was. There were no samples, there was no documentation actually for the structure. And of course, because it's a water retaining structure, taking core samples is not an option in this particular case. So we started with very extensive Schmidt hammer testing on the vertical. So this is how the water reservoir looks like. When I showed you the photograph, when I was looking at the mountain, I was standing on this end, the sort of the north west side of the reservoir, and looking up to the mountain. And so we did Schmidt hammer, very extensive. We mapped it. Ultrasonic pulse velocity testing again took us a lot of time, just because the distance of the probes was not very large. So again, we mapped that for the top slab and for the walls. I must mention that it looks very easy to do it here, but some parts of the reservoir, there are a lot of bushes, there are a lot of trees, and some parts are actually of the walls are not even accessible. The top slab is accessible, but some of the sides are not accessible. In addition to that, we did some infrared imaging as well. So this is not perpendicular images. We just try to lay it on top to see what we can understand from it. Of course, optical imagery. So we have images for different parts to measure any cracking that may be there. So we try to identify surface defects in different places. We use ground penetrating radar here. So try to identify what was not visible to naked eye. We actually got a glimpse of the reservoir from the inside. So every 2 years, the reservoir is completely emptied, and it gets a thorough cleanup on the inside. So we actually were able to time it to get a very good view from the inside, so we could corroborate what we were seeing from outside and what we were seeing from inside. This from the inside, this is a very extensive, very we don't have an appreciation when we are outside. When we go inside, it's a very deep structure from the inside. So in addition to some of the base NDTs that we did on it, we were able to identify certain zones where the municipality should keep a close eye on. But like I mentioned to you before, that the municipality was very interested that what would happen if an earthquake took place. So we know what before the earthquake, but how do we know what has happened after the earthquake? So the second phase of this project was to have some real-time structural health monitoring for them. So a very big suite of sensors. Sorry about the little mess on the text there, but we have everything here. I can spell it out for you, from accelerometers to tilt gauges to of course, strain gauges and deflection gauges, and even crack gauges, for example. So we don't have much time here, but the wall panels that we have on the reservoirs, those are actually precast wall panels. It's not a monolithic construction, and the precast panels are connected vertically with a bentonite water stop in between. So of course, before or after an earthquake, one would expect some movement to take place between the precast segments, and that was something that the municipality is interested. So again, Mount Tolmi Reservoir is close to our university. The mountain can be seen. Sensor location, I won't get into the details. Again, between structural relevance to practically being able to install the sensor. Two, I will just throw an idea here, to vandalism. Like if I have a sensor within reach, this is of course a publicly accessible place, and the top many tourists come to view. So of course, if I have a sensor which is within reach, people would probably vandalize it or break it. So we had to find sensor locations with a compromise between structural vandalism and accessibility. So we did all of that. And again, I won't spend too much time on this. My student Nazrin has been doing much of this. Data visualization is taking place. And finally, some of the takeaways from this particular project is that NDTs were able to be used to confirm that the structure is in reasonable condition. We are actually in the process as we speak to construct a digital twin for the structure, so we can monitor what happens in real time. I will just throw in my own little comment here on health monitoring. I'm typically not that excited by the magnitude of the numbers that I get from the sensors. What's usually of interest to me is what is the change of those over a period of time. So if I have two wall panels in the water reservoir with a gap of 13 millimeters, great. And 13 millimeters means nothing to me right now. The reservoir is good, it's not leaking. But if an earthquake happened and the 13 millimeter remained 13, I'm still happy. If the 13 became 25, I would be concerned about that. So I'm always looking for the change in the readings. Even for accelerometers, what's important to me is the change of the signature over a period of time. So that was the Mount Tolmi, again, a beautiful sight from here. I just want to acknowledge all my grad students and undergrad students and international students, both including coming from India and various industry partners. NSERC, like DST for India, is our sort of a federal government agency. So thank you to NSERC for funding many of the projects that I showed you here. And with this, I just want to thank Dr. Meena Murmu here for thinking about me and for inviting me. And of course, I know it's getting very late in the night for all of you, and it's getting to start of a working day for me here. But I just want to thank all the audience for listening in. And I'll finish off with this last slide. So that's my email address. You can reach me through Dr. Meena, or you can contact me directly at this email. Many of the published work that I presented today, actually from the case studies, except for the last one on Tolmi, are actually available on ResearchGate. So if anybody was interested, you can always request that information. I'm happy to share it. My last closing point is at the beginning, I mentioned that I'm the Vice President International of the Canadian Society for Civil Engineering. And I just wanted to mention that we do annual conferences each year. The date, unfortunately, for papers has passed for the one that we're having right now. But May 28th to the 31st, our conference is in Winnipeg. The one in 26 will go back to Quebec City. So it's a great place to be. So please keep that in your mind. And the website for that is csc.ca. And with that, I'll stop over and pass over the mic to Dr. Meena here.
Thank you very much, sir. Any question from participant? You may ask to experts. Is it audible? Hello?
Good morning, sir.
Good morning.
Yeah, it's Dr. Dada Patil from Mumbai. Sir, I would like to ask how reliable are hammer test results? Hammer test result is it really reliable as compared to other tests, or I mean,
Yeah, no, Professor Saket, a good question here. I mean, the hammer tests are, just in literature, we know that the hammer test could be, there could be a variation of 20 to 30% in the test results. More importantly, I think the magnitude of the numbers don't mean much unless you do a calibration in the lab. Like, so you literally need to bring a core sample, you need to test it and break it to have a calibration. But what we did was the Schmidt hammer was actually just a initial test to find places of interest for us, and then we wanted to follow it up with ultrasonic and GPR, because if we did ultrasonic and GPR everywhere, that would take a very long time. So it's relatively easy, but I agree with you, it's not a very reliable test per se, unless you do the calibration in the lab.
okay, sir, thank you.
Any more question from participant?
Sir, again, me only. What was the maximum compressive strength you got in pervious concrete, sir? Compressive strength after 28 days in megapascal, or I mean.
Yeah, so the compressive strength, the one that I showed you from Vancouver, that was about less than 4 MPa, so 3 to 4 MPa. But I have a feeling, like I was mentioning in my presentation, I think one of the reason is we didn't even know how to make the cylinders, right? Because there was no test standard which tells us how to make cylinders. So what we got from the test was about 3.5, 4 MPa. But if I had to really guess, I think the concrete was more probably like about 10 MPa.
Okay, sir. Thank
you. This much only, or any more question from audience?
Hello, sir. Good evening. I am Ashok Meti. Uh, Sir, what provisions are available for durability of pervious concrete?
Very, very good question there, and that keeps coming up all the time for us is how do we measure durability? And if I can just I know we're running out of time here, but just maybe back up a little bit. Of course, so if you just leave pervious concrete for a few minutes, regular concrete exposed to freezing in North America, we need to ensure that we have an air entraining agent added to it. So our goal usually is to have 4 to 7% air content in our regular concrete. Now, the question that you asked is very relevant, because that question kept coming up all the time, that if I have porous concrete and if I have 30% air voids in it, what would happen if the water is completely full in the pavement? So let's say it rains in the day and it's completely saturated, and in the night the temperature drops to sub-zero. If a situation like that happens, I think it would be very bad, because the ice is going to break the porous concrete from inside out. But I think what ends up happening is the concrete is never fully saturated, because it's of course is seeping down. Your durability question, so there is a freeze thaw aspect. I don't think uh, we as a research community have full answers on the durability of porous concrete. Not only that, I think the raveling is a little bit of an issue. So in our project, we saw more raveling taking place during the first 3 months of traffic. Then the raveling reduced over a period of time, but we did see after about 1 year tire marks on the concrete pavement, which showed where the most raveling had taken place. So it's not 100% there yet. I think there are more research questions for all of us to work on porous concrete.
Yes. Thank you so much, sir.
Thank you, sir, for your lecture, and to participant also. And we have definitely we will contact you for your research also. And sir, that paper was acceptance is over already. Date was for
Yes,
conference.
Dr. Meena, that one is over for Winnipeg. But if I may suggest, you can just keep, if anytime interested in a conference, the conference will always be last week of May or first week of June every year.
Okay.
So moving forward, please keep an eye on it. The call for abstracts usually comes out in September or October. So please aim for the next one if this one is too late.
Yes, sir. Thank you very much, sir.
Thank you very much,
sir.
and thank you everyone. And yeah,
and good morning.
Have a good
sir.
night. Yeah, have a good night,
Good
everybody.
night. Good day, sir. Good day.
Thank you.
So tomorrow I will
Sir,
contact
very nice
you
session,
by
sir.
mail.
Sir, it was very nice session, sir. Thank you. Thank you.
Thank you so much. Thank you for listening.
Sir, could you please provide your email ID? 1 second.
Thank you, sir.
Yeah, I can put it in the chat.
Ma'am, 1 second. Let me take.
I put the email in the chat.
Thank you so much, sir.
Thank you and have a good night, everyone.
Good
day,
night,
sir.
sir.
Yeah, thank you.
Good day.
So tomorrow I will contact you by mail.